Okay, what is up everyone? My name is Samuel Christopher and today I will be presenting on the metallurgy and corrosion control in oil and gas productions. So, in the expansive realm of oil and gas exploration production, the field of metallurgy plays a critical role in ensuring the integrity and longevity of equipment and infrastructure. Oilfield metallurgy involves the study of application of material science principles to design, select, and optimize metallic components that withstand the harsh and corrosive environments encountered in oil and gas operations. One of the foremost challenge facing the industry is corrosion, a relentless adversary that can compromise the structural integrity of equipment, pipelines, and facilities. So the table of contents we'll be presenting will be corrosion control, the first chapter, and the second will be corrosion in terms of chemistry, and the third one will be the corrosive environments caused by that. So with the first one will be the introduction. So what exactly is oilfield metallurgy? Oilfield metallurgy is a specialized discipline that revolves around understanding the requirements and performance of materials used in the challenging environments of the oil and gas sector. The specialized program aims to provide understanding of material specifications and selection specifically designed for the oil field. The knowledge gained facilitates more informed conversations between clients and providers, providing a deeper comprehension of material properties and their influence on the design of components for oil tools. With the cost being the primary avenue for cost savings, the list lies in preventing failures that result in lost production. Just because existing systems currently lack corrosion issues doesn't warrant a reduction in maintenance budgets. It's crucial to recognize that as oil fields age, they may become more corrosive, coinciding with periods of diminished returns on investment. Estimates suggest that the costs associated with corrosion are roughly on par with those related on mechanical breakdowns and maintenance expenditure. With the safety being, hydrogen sulfide is a prevalent component in various produced fluids, posing a dual threat as it's not only toxic to humans but also gives rise to diverse environmental cracking issues. Given that pipelines and other oilfield equipment often function under elevated fluid pressures, the risk of leakage is a significant concern in managing the potential dangers associated with hydrogen sulfide. Lastly, for the chapter will be the environmental damage, which is such oil spills, soil contamination, water pollution, air pollutions, and as well as such economic impact that can actually damage the environment with that being. So the second chapter will be the chemistry of corrosion. So corrosion typically involves the oxidation of a metal, accompanied by parallel reactions that utilize the electrons associated with the electron corrosion process. Although the overall corrosion reactions are often labeled as half-cell reactions, it's crucial to acknowledge the interdependent relationship between oxidation and reduction. This interplay is evident in both anodes, where oxidation is prominent, and cathodes, where reduction predominates, constituting an essential component of the electrical current. So there are some electrical reactions that we provide over here, which will be the oxidation of carbon steel, where the oxidation gains or basically loses electrons in this process, whereas the oxidation reduction in acid reaction is where the acid-base reaction actually takes place, or basically the formation of H2O from oxygen as well as electrons. And then there's oxygen reduction, which is completely the opposite of that, and then the oxidation of carbon steel, which is basically the gaining of the gaining of electrons, and so on and so forth. So the electrolyte conductivity. The resistivity of liquid and solid is influenced by the presence of ions dissolved in the substance. Hydrocarbons like crude oil and natural gas are just primarily covalent in nature, rendering them poor electrolytes. In the context of oil corrosion, the phenomenon is typically induced by chemicals present in the water phase. As water inherently possesses lower resistivity compared to hydrocarbons, this interaction with waterborne substances contributes to the corrosive processes associated with oil-related systems. So the electrical potentials and current, the electromotive force series, which is basically the EMF series, is an orderly arrangement of the relative standard potential for pure metals in standard conditions. The more active metals on the list tend to be corrosion susceptible, and the less active or noble metals will resist the corrosion in many environments. So these are the electric potentials, where E is basically the electrochemical potential of the reaction, and E note is the standard electric potential at standard conditions, and R, which means the Boltzmann constant, and T as in the temperature in Kelvin, and N is the charge of the ion being reduced, and F is the Faraday's constant. So in summary, what do we actually get from chemistry of corrosion? is that corrosion processes an electrochemical character with most metal surfaces undergoing simultaneous oxidation and reduction reactions. When oxidation is a prevailing reaction, the metal tends to corrode. Electrode potentials are influenced by factors such as metal chemistry, environmental chemicals, and temperature. And the following ideas have been discussed in detail, which is corrosion is electrical chemical in nature. Most metal surfaces have both oxidation and reduction occurring simultaneously, and if the predominant reaction is oxidation, the metal will corrode. And the most important reaction is oxygen production for many oilfield systems. If there's no oxygen is available, the corrosion will often be very low. So, in the last analysis will be the corrosive environments. So we actually have such conditions to which corrosion will take place, and one of which is oxygen. And oxygen is a key factor in the corrosion of metals, exerting a considerable influence on corrosion rates. Frequently serving as an oxidizing agent, oxygen engages in electrochemical reactions that actively contribute to the corrosion of metallic structures. This influence is especially prominent in aqueous environments where the corrosion mechanism encompasses the creation of metal oxides and hydroxides. And as you can see on the figure on the right, as we know that as temperature increases, the corrosion rate will obviously increase. This will therefore means that as temperature increases, the corrosion rate due to oxidation has been taking place a bit more because there is more reaction, more collisions and the particles, so oxidation rate as well as corrosion rate will also increase along with temperature. And the second one will be carbon dioxide, as carbon dioxide can actually affect the corrosion of metals, particularly in fermenting with water. When carbon dioxide dissolves with water, it forms carbonic acid, which can corrode certain metals by facilitating the release of metal ions. Corrosion can lead to localized issues like pitting and crevice corrosion. In the oil and gas industry, carbon dioxide corrosion is a concern in the pipelines and the environment. The presence of carbon dioxide can create a corrosive environment, impacting the protective layers and metal surfaces. To address this, industries often use corrosion-resistant materials and coatings to protect metal structures from the harmful effects of carbon dioxide. Same as the previous figure, carbon dioxide has increased corrosion rate with the increase of temperature, but also in the x-axis with the increase of liquid velocity, corrosion rate also increases. And last but not least, it will be hydrogen sulfide. Hydrogen sulfide is a corrosive gas that possesses a threat to metals, particularly in industries such as oil and gas. It induces various forms of corrosion, including sulfide stress corrosion cracking, which results in cracks in stress metals, and hydrogen embrittlement, leading to increased of metal brittleness. Hydrogen sulfide also initiates generalized corrosion by gradually deteriorating metal surfaces. Moreover, it triggers localized corrosion like pitting and crevice and corrosion, forming small holes and crevices. The small reaction between hydrogen sulfide and metals produces sulfide on the surface, intensifying the corrosion process. To counteract these corrosive effects, industries employ corrosion-resistant materials, coatings, and inhibitors, coupled with regular monitoring maintenance practices to ensure the ongoing safety and reliability of equipment. So yeah, that's it for the presentation, and I hope you guys liked the video. So thank you everyone, and good luck.